Well, this is the start of a new set of 12 presentations, not on structure, but on reactions. And most of the reactions that we'll be considering are polar reactions. Now, polar reactions are very prevalent in most of the organic chemistry textbooks that are sold. There are going to be a lot of different functional groups and a lot of different polar reactions that are considered with those functional groups. In this set of 12 presentations, we'll be looking at, and I'm going to switch to blue, we're going to be looking at 4 different functional groups that are going through polar reactions. The first one we're going to consider is the alkyl halide. The alkyl halide has as a structure an alkyl group, let's say an ethyl group, connected to, let's say, a bromine. Now this can be a chlorine or an iodine. Now fluorine's not a good leaving group, so they tend to not use alkyl halides that have a fluorine instead of a bromine here. When mixed with what? Well, what we're going to consider these mixing with to react is a nucleophile. Nucleo meaning nucleus, phile meaning lover. So something that's going to love on a nucleus attacks the alkyl halide or reacts with the alkyl halide. These nucleophiles love something that's a positive. Why? Because they love a nucleus. Nucleuses are positive. They're nucleus lovers. They're going to come after something partially positive in the alkyl halide. That's the first reaction we'll consider. And it'll have 4 presentations that cover reactions of alkyl halides with nucleophiles. And we'll abbreviate this as NU. Second. The second reaction is going to take us in an altogether different direction. We're going to consider alkenes. Alkenes reacting not with nucleophiles. Alkenes have to have at least a pi bond. The alkane is a hydrocarbon that's completely saturated. Alkenes with the E here, are hydrocarbons that have at least one pi bond present. A double bond, which we now know through orbital theory, we have a sigma and a pi bond together that make up the pi bond. That make the double bond. It's a sigma and a pi underneath the double bond. We're going to be considering alkenes with electrophiles. Electro, that's electron. Phile, loving. So we're going to have something attacked by the pi electrons, because these are the richest site within your alkenes of excess electrons, and they're going to attack the electrophile. So the trend's kind of different here. These will be attacking the electrophile. Over here, the nucleophile will be attacking the alkyl halide. So it's sort of flipped. The functional group is being attacked by the nucleophile with alkyl halides. The functional group of focus is attacking. So we're going to have another one just like that also, where we have, instead of a double bond where pi electrons attack the electrophile, we're going to have triple bonds, an alkyne. We'll be looking at alkynes and how they can also attack electrophiles. Things that are, again, loving of electrons. What would that be then? That would be a positively charged species that's being attacked. Here, this is a nucleus lover, so it has to have a negative charge that goes and attacks a positive charge or partial positive charge. So these are sort of opposite directions. Reacting with nucleophiles, functional groups reacting with electrophiles. Last, of the 12 presentations, we'll have 4 here, 3 here, 2 here, and the last 3 presentations will focus on dienes. Dienes reacting with electrophiles, and that's our first one. And we'll have plus dienophiles. So dienophiles would be diene lovers. So we'll have a Diels-Alder reaction that we'll end with. It's a special type of reaction. It really doesn't fit underneath just the rules for polar reactions. A lot of what we'll be discussing, though, do fit under the rules for polar reactions. So what are those rules for polar reactions? Well, just before we get started in all the details, the reactions we're going to be considering, it's probably best to go ahead and to consider the different types of reactions we can have. Different types of reactions that fall under polar reactions. These are very minimal radical reduction oxidation. So the polar reactions will be given the emphasis for most reactions in the 12 presentations. And the rules are: find those electron-loving sites, that would be positive, and find those nucleophilic sites, those would be partially negative or full negative. Find them. And in every step have the NS attacking the ES, the rich to poor. We're going to always consider for every step the rules that guide regio and stereochemistry, where things bond and how things bond. And then we'll draw mechanistic arrows according to what makes sense, considering the ES and the NS. We need to make sure we find those before we draw arrows showing the transfer of electrons. That's going to be the fundamental, I guess, 3 steps or rules you should take whenever you're trying to solve a polar reaction problem. Now, the other reactions underneath polar reactions are not as prevalent in the literature, or I guess you'd say most textbooks on organic chemistry. So I'm just going to cover these rules very quickly, or at least some patterns you typically see. Radical reactions typically have 3 steps: initiation, propagation, and termination. So those 3 steps together. Initiation is the cleavage homolytically of a bond where the oxygens, let's say here, take 1 electron each. And you get radicals, 2 of them. That radical can transfer the radical, that odd electron, to a hydrocarbon. So the radical goes from the oxygen to the hydrocarbon in a transfer process. It's called the propagation. And when 2 radicals meet, that's called the termination step. It's sort of the opposite of the initiation step. These 2 steps are, I guess, the beginning and end. Highest jump up in energy and the biggest jump down in energy are represented by 1 and 3, initiation and propagation, or sorry, initiation and termination. Reduction reactions, we're typically going to be involving hydrogen in a 0 oxidation state or a -1 oxidation state. It typically reacts quickly across pi bonds. These are more reactive than sigma bonds. And if we have a polar bond, let's say a CO double bond, where we have a pi bond between a carbon and an oxygen, then with the oxygen being more electronegative, we know by resonance and inductive effect, we have a polar that would create a very partial positive charge on this carbon. Hydrides, H-, tend to react, of course, negative to positive at those carbons in the pi bond between the C and the O. They tend to attack the carbons. The patterns for oxidation are just a little, I guess, in a very, very simple sense. If you have a lot of oxygens around a metal, those oxygens can be given to an organic molecule where you make, in place of C-C bonds, typically pi bonds, you start replacing those with CO bonds. And the oxidizing element is really the metal. We're, in a sense, delivering the oxygens through chromium oxide, osmium tetraoxide, manganese oxide. Periodic acid is another one that has a lot of oxygens off of an iodine. Ozone and hydrogen peroxide. If you see a lot of oxygens, just start thinking, oh, I may have an oxidation reaction. All right, let's go ahead and come back to polar reactions. We're going to start off looking at alkyl halides. Now, we're going to take a different sort of approach to the discussion of reactions of alkyl halides. That is, again, RX, alkyl halides, plus nucleophiles. A sort of different approach. This is going to be our one slide for the foundational sort of concepts behind RX plus nucleophile and how we can have SN2 or E2 reactions, at least these two. We'll consider more, but these will be the first ones we look at. Just the basic pattern for SN2 and E2 reactions. And then we're going to kind of jump to a sort of a different approach where we look at just designating what Rx we have and what nucleophile we have so we can pick between different reactions. And then we'll go into more details for each of those reactions. I'll show you what I mean in just a little bit. Let's go ahead and finish what the basic concepts are behind SN2 and E2 reactions as seen through the rules for polar reactions. So if we looked at hydroxide as a negative, and make that very pronounced, we would say this being a full negative would be a nucleus lover. So this would be the strongest nucleus lover because there's no one else in this mix of the hydroxide with the alkyl halide that has a full negative and an atom with that full negative that's not, I guess, stable with that, like chloride or bromide. So this is a very reactive anion. It's the greatest nucleophilic site we have, nucleus-loving site that we have. So we need to go find something positive for this to hit. Well, if we go to the alkyl halide, we know that this is electron withdrawing by inductive effect, so we could put partial negative, partial positive, just started tagging structure, not based on resonance, but based on inductive effect. Carbon to chlorine bonds are polarizable. In solution, they're polarized, and we can have partial positive, partial negative charges for the C and the Cl. This carbon then would be an electrophilic site, electron-loving site. So we can now make the connection. We said bonds form. On the last slide we said rich to poor. Find these most reactive sites and bring them together. And we're going to draw now our mechanistic arrow and consider some regio and stereochemistry. With SN2 reactions, we'll learn that we come in where? To the partial positive carbon, connected to the halogen. And as we come in opposite side of the chlorine or bromine or whatever the halogen is that we have here. We come in from the opposite side. That's discussing stereochemistry. So our arrow is showing not only where we hit, but we're sort of also showing how we hit, coming in from the opposite side. So this bond, you say, well, what electrons can we use off the oxygen? Well, any of the 3 lone pairs. The bond is made using 2 of those electrons out of the 6. Now we have only 2 lone pairs left. Those 2 electrons are used to make that bond, whereas these 2 electrons that were in a bond go to the chlorine, hence it has to have a negative charge because it went from sharing to owning those electrons. So we give it a negative charge. That's the basics for SN2. And we're going to develop this reaction more or learn about this in a greater way, but I wanted to offset against that the E2 reactions and then talk about the roadmaps. How do we pick between SN2 and E2 and SN1E1? Well, in elimination, we have to go to beta protons. This is a little less obvious. We still have a strong base or a nucleophilic site, something that would love on a nucleus. And we have a little less reactive electrophilic site in terms of partial positive charge, in terms of electronics. But one thing going for an attack at the beta proton, which is the competing reaction against SN2, is this. It's exterior. These protons are on the outside. So they're more often bumped into by the hydroxide than an interior carbon. So E2 tends to have kinetically favored, I guess, interactions, that we have more of them. Less favored interactions or contacts or bumps or collisions between the O and this interior carbon. So what it lacks in terms of partial positive charge, it sort of makes up for by having a prevalence of contact with the hydroxide. So this starts to be ripped off, this acting as a base. These electrons have to go somewhere. We don't want to leave them on this carbon, having a full negative on a carbon here. That would be not stable, or that would be very unstable. So we take those electrons to a pi bond and we kick off the chlorine. These two electrons go with the chlorine. So these two go with the chlorine. I'll just say those to the two. It already had 3 pairs, and we have now another pair. That breaks away. We make a pi bond. These two electrons going from sigma bond to pi bond, and we also have the formation of water. So alkene is formed. We have a non-polar product. That's important because what will happen is if we have E2 reactions occurring, these non-polar products tend to boil out of the solution very readily, and that can actually drive this reaction and make it more favored than the SN2. There's going to be some competition between these two, and we can favor one over the other by doing some things or setting the conditions such that we favor driving this off. What conditions would that be? Higher temp. Second, if we form 3 things, it has in general a greater entropy than just forming 2 things. So higher temp also favors formation of more disorder, 3 things versus 2. So we can start to favor E2 over SN2 if we go to high temperatures. Alright, that said, those are the basics for SN2 and E2 reactions. We're sort of getting a look into the concepts behind these 2 types of reactions. I want to take a step back a little bit and just say something about a rubric that we can use to determine whether or not we have SN2, E2, or what we call SN1E1. So I know this is a little bit of ahead of the game, and you say, I don't even know what an SN1E1 reaction is. But let's just think of it as you're coming up in your car to a sign where you have a certain Rx and you have a certain nucleophile, and you need to know which way do I go. Which direction do I go in? What reaction do I consider? Do I go SN2? Do I go E2? Or do I go SN1E1? These typically come together, the SN1E1. They share a lot as far as the road you journey down. So we're going to look at choosing right now from the last 5 minutes which way we go. So the rubric, there's a lot of them out there. I'll have it on the next slide. We can tag the alkyl halide, and if we have a certain alkyl halide, and we can tag the nucleophile, and if we have a certain nucleophile, then we choose according to those classifications that we have for the alkyl halide and nucleophile. Now the alkyl halide is usually tagged as primary, secondary, or tertiary. The nucleophile is typically tagged as strong base, weak base, or non-base. So examples of this would be hydroxide, a weak base would maybe ammonia, and a non-base might be water. So weak base, non-base, and strong base. The alkyl halide, we can tag that as primary, secondary, or tertiary by circling the carbon-halogen bond. You circle that. However many carbon-carbon bonds you cut tells you whether you have a primary, secondary, or tertiary alkyl halide. In this case, I only cut 1. So this would be a primary RX. Primary RX because we only, in the circling of the CBr bond, we only cut 1 carbon-carbon bond. If we'd have cut 2, it'd be secondary. If we'd cut 3, it'd be tertiary. So I've tagged, I should put that down here. So primary RX. Tag that. Okay, I see the sign. There's my alkyl halide. It's on the sign, and I tag it primary RX. Now the nucleophile. We're going to learn that this is, a sodium azide is a weak base. So you would tag your RX, you would tag your nucleophile. This is negative, this is positive. It's the most reactive nucleophilic site. This is just our solvent. We tag it weak base, primary RX. We're going to learn on the rubric on the next page we discussed. That's SN2. So we start driving down the SN2 road, and we do all the things that are I guess, part of an SN2 reaction. So what I'm doing with the first 2 pages here, or these 2 pages that we're talking about, this and the next, is we're just trying to figure out which direction we're going in. And then we would walk it out, drawing the SN2 product. And just so you know, in this case, that would be our substitution product, SN2, where the azide substitutes the bromine. This would be our SN2 product. Now I want to sort of end with this rubric, and there are many out there, and just go in the next recording to application of this for SN2 and E2 reactions. But let's go ahead and set for the substrate, or Rx, and this nucleophile, the strong base, weak base, or non-base, the different categories and the outcomes. An unhindered primary Rx is much like what we just saw. If it's a primary Rx, because we only cut through one carbon-carbon bond, and this carbon at the beta position is either a CH2 or CH3, then that primary Rx is unhindered, meaning there's nothing big hanging off of this beta position. It's just a CH2 like it is here, or it just ends there at a CH3. That's an unhindered primary Rx. If we have that and a strong base, and those are listed below here, your strong bases, so Grignard reagents, sodium salts of alkanes, and organolithium reagents, acetylide anions, basically O's and C's and N's with a full negative, having no resonance to localization. They're strong bases. They give SN2 product. Now if we have a hindered primary or a secondary, this is not hindered secondary, but a hindered primary or secondary or tertiary Rx, starts to get a little bit harder to find the interior carbon. We start to get E2. Any Rx except methyl halides or methyl bromide, and one of these bulky strong bases, they bring the bulk, we have an E2 reaction. Going on down to weak bases, so we have strong bases. If we use weaker bases like those amines, or a sulfide or dialkyl sulfides, or any other anions other than the ones listed here, any other anions, so azide, the azide that we saw here would be any other anion. It's not one of those listed here. So those other anions, the amines, the dialkyl sulfides, those weak bases start to go SN2E2 in a little more liberal sense. SN2, if we have any primary or secondary, it's not such a strong base that it wants to start going E2. It'll allow for SN2 and a wider range of alkyl halides being allowed to go in an SN2 reaction because they're a weaker base. But if that alkyl halide gets a little too bulky, can't find the carbon, becomes tertiary. Tertiaries, RXs with weak bases, favor E2. Secondary or tertiary with bulky weak bases tend to go E2. Lastly, if we have protic solvent, water, ethanol, alcohols present, the secondary and tertiary RXs with weak bases or non-bases, non-bases are alcohol or water or carboxylic acids, if protic solvent is used, that is a solvent that has OH or NH bonds, typically we're looking at OH bonds in the solvent, like water, then we have SN1E1 starting to be favored. If the solution again is protic, the RX is secondary or tertiary, and the nucleophile is a weak base or a non-base. Well, that's the rubric. I'm going to stop there. It's quite a bit to chew on, but we're going to use this rubric now in the next presentation to not only set the roadmap of where we're going, but also start looking at specifically the SN2 and E2 reactions and how we draw those products. Bye-bye.